morning we've got an exciting two-part workshop that we would like to kick off, and thanks for joining. Before we do get started, however, let me just quickly kick off with an acknowledgement of the land on which we are and the custodians of that land, the Whadjuk people, their elders, past, present, and emerging. And with that, we've got Marco Delapierre, who is going to be leading this discussion, joined with Pascal, who you got your video on there. Want to give a wave?
I'm trying to get it on.
Oh, you should. Okay, he's got a Unix system, a Linux system. We're trying to, you know.
Normally this works.
It doesn't always cooperate. And then we've also got Alexis, who is also joining us. And so lots of experts in the room to answer your questions and to work through pipelines, etc. So it is a small group. I'm assuming that if they have questions, you're okay with just having them speak out. They don't have to put it in the chat or anything.
Yeah, I mean, there is a chat just in case. So I added all of you to the containers channel in the Pawsey training Slack workspace. We might not need it today, but yeah, it's there just in case.
And that's a good thing to connect with each other after the session, tonight, whatever, you can continue. That's an ongoing open Slack channel for you to communicate with each other and with us. So with that, we'll turn it over to you, Marco.
Yeah, thanks, Anne. Yeah, and also thanks to Alexis and Pascal for joining today, and to you for being here. So I want to start from the recordings that you might have watched in the previous days. So one good reference website to retrieve the growing set of Pawsey materials on training topics is Pawsey. I'm sorry, I'm going to start sharing the screen. That can help. Here we go. So yeah, so the website pawseysc.github.io is just a landing page for our training materials. So there is a tab on containers, and so let me start and point to the materials I referred to you for some self-paced study. So I just suggest you to have a look at the basics of Singularity, how to run a simple application in the case of Blast, and then how to build containers with Docker. The menu for today is a Q&A session on these videos, so that we can first have some discussion and conversation on the basics of Singularity and for running containers on HPC, and Docker for building images. After that, there will be about 1 hour of materials that I prepared just for today, just for you, which focus on Python containers, with a focus on building best practices and HPC specific topics. And that would bring us hopefully to about 11:30. Then we'll have a break, and then we're going to start and have a look at some of the pipelines that you guys are working on. And then the rest of today and then tomorrow's session will be focused just on what you guys are doing. We've kind of an open room for discussion, and Pascal will ping in from time to time. So I work with containers a couple of years, but I know very little about radio astronomy. So he's the guy here at Pawsey for radio astronomy right now. So I'm very glad that he could make it today, because I feel my back covered a bit more. So with regards to these recordings we've seen, I'd like to take any questions that you might have, or any curiosities or points you'd like to get clarified about running containers with Singularity, the basics, building images with Docker, and then we start from there. So if any of you has questions, just unmute yourself and go for that. Okay. Silence. At this stage, it seems like a good sign, hopefully. So have all of you had a look at the recording? So I'm just asking so that I can assume that that part of the of the story is kind of covered. Good. So maybe just to be sure, and let me just open one terminal. And just show you something. So just to be sure we are on the same page, we have singularity pool is the command used to download containers. When you prepend the prefix docker // you're pointing to Docker Hub, the online registry managed by Docker, which has lots of useful images already available. So this is how you retrieve images. And then there is the usual output, which shows the steps of the conversion from Docker format to Singularity format. And that's because Singularity uses a different format to store images compared to Docker. Docker is a multi-layered format made up of different bits and pieces, which is kind of good for, it allows caching. So it's good when you're building the image, because you can, if you have bits that are the same across different images, you can just reuse those. And the Docker does that for you. And so you kind of save time, and that can be quite useful in the process of developing a container image. Whereas Singularity takes the approach of consolidating all of those layers in a single file, which is good for a number of reasons. Security is much easier to cryptographically sign and verify these single files. They're also easier to share and transfer because it's just single files. And they, as of Singularity 3.x, the files by default with .sif. And so Singularity pool is the command to pull images. Singularity shell allows you to open an interactive bash shell in the container. Remember, when you're using Singularity shell, you can either launch a local image file or still go for the repository format. And in that case, we'll try and point to the online image, but if it is already present in the Singularity cache locally, we'll just use that. So you won't re-download it again. And same story. So this is if you want to open an interactive shell. If you want to execute commands, it's Singularity exec. And same thing. And this is executed inside the container. So this is really the basics for downloading and running containers with Singularity. One interesting bit is about bind mounting directories inside the container. So let me do it. So by default, my Singularity installation does not mount home. So if I do Singularity exec Ubuntu image and then ls home, I won't see anything. So if I want to access a host directory explicitly, I can bind mount it with -b. All right. And so this is just a 2 minutes refresher on some things that you saw on the recordings. The other bit I want to show you is about a Docker file, a very basic Docker file. So let me just retrieve the one example from the episode 6 in those tutorial recordings. This is a minimal one, a silly one. It just installs a bunch of funny Linux commands that allow you to have a colorful cow that cites novelists. So, but this is useful just to remember what are the basic keywords you need in a Docker file. Is to specify the starting image for your build. In this case, you're building on top of a Ubuntu based image. There's no restriction to that. That image will be retrieved in an online registry. So as long as you're picking an existing image in the registry, you can start from wherever you like. And we're gonna get back to this point later. Another key command is run. It's the command. It's the keyword that you use in a Docker file to specify instructions to be executed at build time. So you typically use that, for instance, to install Linux Linux packages with apt, or even to build, if you've got a compiler in the image, even just to run a full build, like configure, make install, or using CMake or whatever, pip install if you've got a Python image, and so on. But this is one of the most used keywords or Docker instructions in a Docker file. And then a quite important, useful one is env, which is used to declare variables that need to be defined at runtime in the image. I'd say with from, run, and env, we are covering 95% of the needs in a Docker file. So then just to get back to a point that was in the recordings, why are we using Docker files and Docker for revealing and not Singularity? Well, as I've just said, the two tools use different image formats. And it happens that the Docker one is much more popular. It was the first one that came out, so everyone has been using that for years. And the other thing is that you can run a Docker image with any container runtime, including Singularity, Shifter, Serus, Charlie Cloud, whichever comes to your mind. On the other hand, you can only run Singularity images with Singularity. So there's a much wider compatibility that you gain if you use a Docker format. So that's why we're sticking with that. So the type of workflow and working strategy that we suggest for containers at Pawsey is to use Singularity on our HPC system, so on the cloud or wherever you like, for running containers, and Docker to build those images locally on your workstation or laptop or on a cloud instance. And with that, let me show you the materials that I prepared for you for today. Before I start, do we have any outstanding points, and Pascal?
No, I think we're good.
Okay.
I think we're good.
And guys, if you have any questions, feel free to unmute and ask. So now I'm gonna go back to pawsey.github.io. And in the containers tab, I think it's the fourth line here. So it is using containers with Python in radio astronomy. This is some fresh materials that we're going to go through with you today. And you can get there from that landing page, or if you want to type a lot, this is the full address of pawsey.github.io/containers-astro-python-workshop. And I'm gonna put the link on Slack for you, just in case you need it explicitly. Here we go. So this will keep us busy for no more than 1 hour, because I don't want to spend too much time on this part, because then I'm interested in seeing what you guys are trying to achieve with containers. So this first bit, it is some preparation, of course. So if you've got a machine with Docker installed, you can download the materials as well with Git. So here is the command. And can I just ask if everyone has got a Docker machine available for this workshop or not, just to know?
I don't have one. My computer's being refurbished or something.
Ah, okay. So do you?
That should be all right.
Okay. But just out of curiosity, do you think is it something that you're after getting installed later on, or is that's completely out of your radar?
It's something that's, well, Docker's already installed on my computer at Kyra.
Yeah.
But yeah, at the moment, I think I'll be all right to watch you guys work and just get an overall idea for things.
Yeah, I think you will be fine in case you don't have it. So I'm gonna go hands-on for some parts, but all of what I'm doing is also documented in these tutorial pages. So you guys can get back to this link at any time, and it will be there for you to review. So even if you can't do it live, it should be hopefully still be useful.
Okay, yeah, thanks.
So this is one little thing that depending on the configuration of your Docker, you might or might not need to do. I find it quite handy. So because Docker needs administrative rights to execute anything, in principle, you're always required to run every command with sudo prepended, otherwise the command will fail. I'm becoming more and more lazy when I type stuff in the shell. So I find it useful to bypass this just to save some typing. You can, when you install Docker, a Docker Linux group gets created. So if you add your user to this Docker group and then log out, log in back to the machine or to the terminal session, you won't need to prepend sudo anymore. So Docker will still use administrative rights to run, but at least you're saving those 5 characters of typing every time. And so you won't see any sudo in these materials because of that. Like in the Mac, that's default. You do not need to do that, but in a Linux box, normally you need to set this up yourself. Just a general principle that kind of underpins our way of suggesting container usage at Pawsey. 2 typical approaches. So 1 container per application, or 1 container for the whole software stack that is behind the workflow. So when to pick one or the other one. So there are lots of workflows in other domains, such as bioinformatics, for instance, that make use of a number of standalone packages, typically written in C or other low-level languages. So all of these packages are kind of independent of each other. They rarely have common dependencies when you install them. So in this case, we typically recommend 1 container per application because this in general is simpler to maintain. Say you have to fix something for a given application, you don't have to take care of upgrading or touching anything related to other applications. And it's also more modular. So say you have a workflow, you're using 10 applications. At some point, you realize that for one of the tasks in the workflow, you need to substitute one package with another one because it works better, it suits your needs better. If you have a monolithic container, you need to rebuild everything. If you have 1 container per application, you just substitute 1 container and it's much easier to maintain and redeploy. However, this doesn't always work. And that's specifically the case for Python and R. So in this case, when you have a workflow that is heavily based on these languages, you might end up needing a number of packages written in this language. And typically in Python and R, these packages bring a number of dependencies. And I've seen that a lot with R, but in Python it can also happen. Say for 1 package, you might even need tens of dependencies. So if you now need to install 10 packages for a workflow, it means that your dependency tree can grow quite a lot. And if you are building, say, 10 separate containers, 1 per package, you're just multiplying and duplicating these dependency trees, I'd say unnecessarily. So you are making your stack to maintain much more complicated and then hard to have working as it should. But also there are quite good chances some of those dependencies are the same for different packages. And so you might end up having 1 package that uses version 1.1 of a given dependency and another package using version 1.2. And then you may end up with a workflow that provides inconsistent results because it's using inconsistent versions of the same package. And this just as a consequence of this kind of complex dependency tree. So in this case, it is when we recommend to build a single container that includes all of the Python packages or all of the R packages required for a given workflow of your own. Of course, there might still be exceptions to this general rule. You might be in a case where really you have 2 packages with clashing dependencies, so you have no choice but to maintain 2 separate installations. And that's actually a very good advantage of using containers, because if you have that issue, and if that is the issue, you can just build 2 containers and you're good with that. But unless you really need to, I would recommend for Python to just go with 1 monolithic container for your entire workflow. And I know that some of your workflows are kind of hybrid in that they have some Python and some non-Python applications. We might get back to that later when we have a look at your pipelines. In general, I would say maybe a wise choice, but might be to go hybrid. And so I have the Python container, the monolithic one, and then still maintain independent containers for the other applications. We're gonna hopefully see examples with your pipelines later. So now just a couple of little caveats about runtime of containers in Python. I'm just gonna go through this on this page, but don't worry, in a few minutes I will flip to other topics and then just also start some hands-on, which is hopefully a bit more interesting than just scrolling, just watching a scrolling page over and over. So just bear with me for a few more minutes. So one caveat that it's worth mentioning is about the shell environment. So because Python is often used in systems as a system utility for services and other tasks, it is common to have Python variables defined in your host already, regardless whether you're using it for your scientific computing purposes or not. That can be an issue with Singularity, because unlike Docker, Singularity typically enforces integration between container and host over isolation, which in this context implies that all of the environment variables from the host are by default passed onto the container. With Python, this can bring to unintended consequences, just because the Python variables that you have defined in the host just have nothing to do with what's in the container itself. So just to show an example, and this happens to me on Zeus, for instance, or other Pawsey system. On Zeus, there is a Python startup variable defined by default when you log in. And so if you just spawn a simple Python based container that you can grab from Docker Hub, this is Python 3.8-slim. We're going to use it a lot in the hands-on later on. You're getting this warning. It's complaining because it can't find the Python startup path that is defined in that variable. And this is, I mean, this is not a problem. It's just a warning. But I've also seen several instances where this type of crossover between host Python and container Python is causing errors in the pipeline. So to be safe in this regard, there's just a simple thing to do, which I keep on forgetting to do myself, but it's simple enough to recommend at least. So there is a --cleanenv or a --e for brevity flag in Singularity, so that if you run Singularity exec -e and then your container and commands, you are running the container in complete isolation for what concerns the shell environment. And then you see that in this case, the Python startup variable is still defined, but you're not getting the warning anymore. So this -c, hopefully I remember to put it in all of the Singularity examples in these materials. I fixed a couple yesterday evening, Pascal. So hopefully it's everywhere now. But yeah, it can save your day, especially when you're in production stage with Python containers. But then if you use that, so then the next question is, how do I pass variables that I do want to pass to the container? Well, Singularity has got a syntax for that. So you can, in the host, you can define variables that start with Singularity env _. And this is just a very plain example. Variable Singularity env _ variable equal to value. And if you define this variable and then you try and visualize it inside the container, so here I'm executing a command inside the Python container, and the command is this one, and I'm using bash -c before the echo variable command because I want this $variable to be interpreted inside the container and not as the command is being read by the host bash shell. So I'm just visualizing the value of this variable inside the container, and because it's defined this way in the host, I'm getting the value inside the container. So this is how you can pass variables that you really want to pass in a container, even when you're working in a shared environment isolation with the -e flag. And then one last runtime little tip with Python, which actually applies maybe more often with Python containers, but you can use it in any instance. So by default, in a lot of systems, and this should be the default in all Pawsey HPC clusters, and also maybe, not sure, 100% sure, but also in the Nimbus Ubuntu images. By default, the home directory is not mounted in at Singularity runtime, and that's to kind of enforce some security, some more security. So in the home, you may be having sensible data such as SSH keys and other private data, and especially if you're running, say, a public exposed session from the container, such as a Jupyter notebook or something like that, those data might become available to people you don't want, you wouldn't want to have access, that shouldn't have access to them. And so your home is typically not available, and we actually advise not to make it available in the containers. However, some packages need to write stuff in the home. Some just use it as a little, you need to store temporary data or config files or service files. So in that case, and you know that a Singularity container is read-only, so Singularity cannot create the home itself if it's not there. So if you really need a home, possibly the simplest and most versatile way to achieve that is to create a directory in the host, just calling it fake home in this example, and then use the -b, the binding flag, to mount that fake home directory as your $home in the container. And that way, that's it. When the container runs, it has some home directory where it can write files in if it needs to. And as a byproduct, as a benefit, you also get those files persistent across container sessions because that directory is in the host. So if you create a file in the container, you have it available later on, even in the host. If that is unintended, if you don't want that, you just get rid of it, you just clean up that directory after running. But if you do need to store those data, because maybe, I don't know, maybe it's some configuration of a Python package or another package, so you want that persistent, you can just act that way and have it available across multiple sessions. And that I've seen that useful in a number of occasions when running containers with Singularity. So this was just supposed to be a very minor introduction to get us kicked off. But if you have any questions, feel free to unmute and ask.